Good afternoon. Okay, so I apologize for being between you and lunch. Well, if we're lucky, we'll end a few minutes early and we'll get you to food as quickly as possible. I also have to apologize because my talk is a little bit of a lie. I say it's the illest of the ill because I really like the pun, the play on the words, but I'm not actually going to talk about like one IL being better than other ILs. I'm Cyphertext. I'm a former a lot of things. That basically means I'm a has-been. I'm currently a hacker trying to learn how to be a developer. I'm one of the founders of a company that builds a software called Binary Ninja. It's a reverse engineering tool. So I'm curious who you are, though, because that'll help me understand how this talk should work. So if you can raise your hand. First, everyone raise your hand so I know you're awake. Everyone raise your hand. You'll all have to raise your hand. Thank you. That's how I know you're paying attention. Okay, now, who has done binary reverse engineering? Put your hands up. Excellent. Okay, who has written their script or code, something to do reverse engineering for them? About the same number. And who've used an IL or an IR for that process? Okay, so we have a chance to convert some of you. That's my goal. And who's used a decompiler before? If you've used a decompiler before, you've used an IL as well. You may just not have known it. All right, so this is the premise of my talk. I promise it's the only slide I'm going to read verbatim, but I do want to go through this. So this is sort of like my pitch. This is what I believe to be true. First, reverse engineering is fundamental to understanding how software works, right? That's what we do. And intermediate languages are fundamental to how compilers work when they build software, and therefore intermediate languages are fundamental to how reverse engineering works. So that's the pitch, that's the premise, and if I convince you of this, at the end you're going to come out excited to do your reverse engineering, use intermediate languages. All right, so we're going to talk about ILs. I'm going to explain sort of why they are a good form for doing reverse engineering, show some examples of working with them, and then demos of a couple of plugins if we have time. A very brief introduction of intermediate languages. First, in terms of terminology, I'm going to use intermediate language, IL, and intermediate representation synonymously. Some people don't. Some people will think that one is more appropriate than the other. We can have that argument over drinks if you like. But virtual machines, P-code, you'll hear a lot of these terminology. Essentially, this is a representation of a processor or an instruction set of language that exists between source code and machine code. It's somewhere in between. Right? That's basically what we're talking about. If you've taken a compiler class, you're very familiar, you remember that process of how it works. There's a lot of trade-offs in terms of design of intermediate languages. And again, I'm not going to cover that in this particular talk. I just want to say that you'll see certain intermediate languages, intermediate representations that will choose one of these over another as more important. And no decision is wrong. It really depends on what's the goal. Like, what is the purpose of that intermediate language? There are some relationships, though. For example, if something is very verbose, it's going to be harder for a human to kind of read and understand. But it might be simpler to lift. It might be a simpler instruction set. But obviously, the simpler your virtual instruction set is, the more complicated your translation between source code native instructions are going to be. So there's these trade-offs that are involved in all of them. These are just the intermediate languages that are used in reverse engineering technologies from like a security perspective. There's actually hundreds of intermediate languages that are used all throughout compiler design, computer science in general. So this is the small list. And I'm not going to talk about most of these because obviously it would take more than 5 seconds to talk about each one. But I will highlight a summary of a couple of them. So the one that most of you are probably most familiar with, even if you don't know it, is microcode from hexarrays. So the IDA reverse engineering tool has had the hexarrays decompiler out for many years now. And just recently, last year, they have actually kind of opened up their internal design of their microcode and how it works. And so we know a little bit more about what's kind of going on behind the scenes, and you can now access it via APIs. So you can see at the top I've got like it's a disassembly, and at the bottom we've got the actual microcode that it's been translated into. The IDA microcode is not necessarily meant for human consumption. It's not meant for you to sit and do your reverse engineering on top of it, but it still makes a better platform for writing your plugins. You may have also been familiar with using like the C-tree structure if you've written hexarrays plugins before. C-tree is a IL-like representation of your C source code, right? And so it's still a programmatically reasonable thing, right? You don't want to take your binaries you're analyzing. I'm cheating ahead to a couple of the slides, but that's okay, I'll bounce around. You don't want to take your binary that you're analyzing, lift it all the way up to some C source code as text, and then write your plugin. Because one, now you've got to go parse some text, and what's the point of that? You're going to go down to like an AST. Well, you already had an AST before you generated that text in your decompiler. In IDa's case, that's what they use is C-tree. Other platforms are going to use different intermediate languages to do that. There's 72 instructions. Lifting is very verbose. Then it's optimized, and several passes are done on it. So Binary Ninja, the product that I work on, is known for having more ILs than any other tool out there. We actually have 7 at current count. I think we'll probably end up around 10 or 12 by the time our decompiler is done. Because our philosophy is different ILs are useful for different purposes. And so we should have different ILs, right? There's no reason not to. There are certain questions you want to ask where you care about the stack layout, for example. And then there are questions you want to ask where you don't care about the stack layout. For example, when you write some C, you don't tell the compiler where things go on the stack. Now, yeah, implicitly you might, based on whether it's a local or, there's certain things you can do to control where it ends up. But those can change with compiler flags. The source code doesn't determine the stack layout directly. The compiler does that. So when you're reverse engineering, you may or may not care about the stack. And so this is one example of why you would want different intermediate languages. Quick summary of kind of how we do things. I'll show a couple of quick examples. Here's what low-level IL looks like. You'll notice one of the things that's unique to our intermediate languages over most other intermediate languages is that they are designed for people to read. We actually want to encourage people to do reverse engineering looking at ILs. You don't have to know as much about the architecture semantics, and you can still understand it looks more like kind of like a pseudocode. But then we have representations that are meant for automated analysis. So here's, for example, our medium level. It's more abstract than the low level. You'll notice it goes from yay big, it actually shrinks. So the higher up we go, the more abstract we get, the less detail we have in the sort of the higher level the summary is. And then you have one that actually gets much bigger, and you wouldn't want to look at. Like, that's obnoxious, right? So this is our mapped medium-level SSA form. I'm not going to talk about the details of that. Find me afterwards if you want to know like the differences behind that. But this is meant for your scripting. This is meant for you to write code on, and it actually enables several types of analysis where you can do static data flow and you can do parameter tracing much more easily than you can in the other forms. So it's good for your automation, but it's not good for you to manually reverse engineer. Okay, ILlest is the intermediate language used by Redair, and it is very concise, so it makes it denser than some of the other ones, but it's also postfix notation, so it's still kind of hard to read. Trying to parse that third line, for example, I can't do. My state machine and my brain is not good enough to easily do that. So it's not great about that representation. It also, as a string, sort of loses some of the value in terms of writing plugins on top of it. Certainly you can do it, but now you're doing string parsing and then compiling it back down. So I would like to see them to change that, I think, to make it a little bit more accessible for automation. P-code is the newest IL out there. It's from the Ghidra reverse engineering tool that was released relatively recently. You can see that this sort of, I would say, is a middle ground. It's not quite as readable as maybe BNIL, but it's certainly much more concise than the microcode or any of the Vex and BAP and any of the other kind of ILs that are out there tend to be very, very verbose, and they'll fill up the whole screen of intermediate language for one native instruction. And it also is supported many architectures, and they have the definition files, so you can go and see how they've parsed it. Okay, so great. There are ILs, so what? Why should I use them? I hinted a little bit earlier in terms of why you might not want to use source code, but why don't you just write your plugins parsing the native assembly, right? In fact, many people do. Many plugins would just say, well, if I want to know what this syscall is, I'm going to go look for the syscall instruction, and then I'm going to look at this particular register which contains the syscall number, and I have to scan back up to look for that register, find that value. Oh, it came from some other register, and I have to go find that other register and see where it was set to what value. So it requires a lot of work for you to write this kind of parsing. With an intermediate language, that can be much, much easier, because the tool that does the lifting takes care of the calling convention for you, for example. So you can say, at the moment of a syscall, what is this syscall? What's the parameter of that syscall? What's the first parameter of that syscall? I don't care if it's a register, I don't care if it's a stat, I don't care where it comes from. Let the analysis platform that I'm using answer that question for me. So you get to sort of take some shortcuts in terms of this. Additionally, you have a much smaller set of instructions. x86 sucks to write a parser for, right? If you've got to handle every x86 instruction, that's a lot of work. If you've got to handle only 72 instructions in microcode, or an even smaller list in many of the other ILs, it's much, much easier for you to write a parser for. And then as an added bonus, when you've written your plugin, it's not cross-platform. Right? If you write to an intermediate language that supports multiple native architectures, you don't have to rewrite it every time that botnet now migrates from MIPS to PowerPC or whatever other platform it's running on. And so the intermediate language gives you the sort of like the appeal of Java, right? Like the original pitch was you write it once and it runs everywhere. So you can get a universally bad GUI no matter what platform you're running on. But anyway, with the intermediate languages, though, that's the pitch as well. The idea is that you can write your analysis and then have it be portable to both the operating system, the CPU architecture, which is convenient and saves a lot of time. OK, so why don't we do a decompiler? All right, I mentioned this already a little bit earlier, and I said that source code is actually not super great to parse. C source code is the form that we as reverse engineers like looking at, and we're used to looking at. I think IDA in particular deserves credit for really improving state-of-the-art in reverse engineering and making it so that we as reverse engineers have access to source code when we wouldn't have otherwise, and importantly that it's an interactive process where we can improve the state of analysis. So we're used to that being the best representation of our knowledge. But the point of reverse engineering, though, is not to get to source code. Right? That's not actually the goal. The goal is for you to understand the program, whether it's because you're trying to find out the IOCs, whether you're trying to extract out CNC information, you're trying to find a vulnerability, whatever you're trying to do, you are trying to model the program into your head so you understand what's going on and you can answer questions about what it is doing or is not doing. Right? And if C is the best place for that, great, do it with C. My argument, though, is that C is not actually the best way to do that when you want to build automated code. Because, again, now you've actually got to kind of parse that C code out. OK? So, and again, if we look at the process for compiling software, we start with source code. We go down to some intermediate languages. No matter what compiler you're using, they're using one or maybe many intermediate languages. And then they go down to the machine code. When we're doing the reverse, we had this intermediate language that is itself very parsable, whether it's an AST or postfix notation, whatever it is. It was built for computers to parse. And then when we turn it back into C code, now we're turning it into something that's more for humans. So write your code for computers, not for humans. All right, working with ILs. Like if we've actually got an intermediate language, what are some of the differences that we're going to encounter? So first of all, I'm going to talk about the Binary Ninja IL because that's what I'm most familiar with. Different ILs have different structures. It's tree-based. So that does mean you're going to kind of have to walk expression trees. Now, in this case, it's a call, so it's fairly straightforward. But you can see it's a call IL operation. It's an enum you can pull out to get the type. And then there's a destination, and it's a constant pointer. And then the actual value of that constant is the actual value. So you've got to kind of like walk down this tree if you want to check the properties. This one is a little bit more complicated. Now we're actually going to show a medium-level IL call. And it actually gets more complicated because it's going to take into account the parameters. So we're now turning that call instruction into a call with the function that we're actually calling with the parameters to that function. And you can see we've actually kind of got to walk this out. So you need to either build some sort of visitor code, or you need to recursively traverse through this structure to kind of get what you want. So you're not just going to be like grepping for strings to look what you want. You're actually going to be walking this kind of structure. I'm going to actually show that briefly in one of the two plugins. So there's two plugins that I'm going to demonstrate here shortly. I actually planned to write one of them and found out somebody else already had, so I got to be a lazy presenter. And my goal was to do two different tasks with an intermediate language that are common reverse engineering tasks or that would help your analysis and demonstrate how you would do that on the intermediate language. The first one is there is a plugin called CryptoScan that was CryptoScan was actually written by Ben, who posted this plugin for Binary Ninja at least a year ago, I think. Yeah, it was 11 months ago originally. And the idea is very common task, right? You've got a bunch of crypto constants defined because nobody wants to like reverse SHA again. Once you've done that once, that's enough. You don't want to actually have to reverse engineer cryptographic functions if you can help it. And so having a library of constants that are commonly used in cryptographic functions to be able to identify them helps you not reverse engineer things that you can just summarize and just name your functions and move on. So we built this function, and it would just scan through the binary looking for these bytes. And one of the things that I pointed out to him a while ago is I said, well, you should be using the intermediate language because there are actually certain platforms, for example, where they do split loads. And so in some architectures, if you want to load a constant to a register, it's a fixed width instruction. You're only going to load the upper, and then you're going to load the lower as two operations. And so you're going to get, say, a 32-bit value in the register. Man, that's scary. They don't tell you about that. I mean, they tell you it's coming, but not that it's going to catch you. So you're going to get this full 32-bit value loaded in, but you're not going to see in the disassembly, right? You don't see those 32 bits in the raw bytes of the binary because it's loaded part-wise. And so if you do it on the IL, you don't know. You just have to scan through the IL, and you're just looking for constant kind of values that are loaded, and it's already taking care of that for you, right? So you get that sort of for free. So it turned out Ben had already actually, between the time that I had looked at it and added this to our plugin repository and the time I submitted this talk, he had actually added the IL scanning on it, and I had missed it, so I didn't have to write that part. But if we look at the code that he wrote here, there's this recurse retrieve constants. And so I mentioned earlier, when you're working with an intermediate language, there's several ways you can approach it. This is fairly straightforward. He is just doing a recursive operation where he is looking for an MLIL const type. And if he finds it, he appends it to the list of all the constants he's extracted, and then he has a separate pass where he goes through and looks through his database of all the crypto constants and matches them up with the constants that have been found. All right. So let's talk about the other plugin. The other plugin is the triage plugin. This is something we actually just built recently in Binary Ninja, and it is designed actually for malware analysis. We got some great feedback from some folks who said, listen, Binary Ninja is a nice tool, but like I need to be able to very quickly make decisions about binaries. I need to be able to analyze them very, very quickly. I just need to get a summary of the view. I need a bunch of high-level information. And we said, that sounds great. We're all mostly reverse engineers for vulnerability research, and so we had less experience with malware analysis. Like, what features do you want? So they gave us this list. We put together this triage view. It's a little bit small. I apologize for the font size, but you'll see there's like an entropy map up top. There's symbols with timestamps and compiler, all the usual section headers, things that you would want. And importantly, we have a list of imports and exports right here, for example. And so this particular list of imports and exports, can't really see a whole lot, but you'll see all the different modules. You see the ordinal that'll be there. But if you've ever reverse engineered a piece of malware that like dynamically loaded any functions, they're going to use dlsim on a POSIX platform, or use getProcAddr, for example, on Windows. They're going to load a function by a string argument, and then let the library actually load it up, map the address in, and then they can call that function later on in their code. That sort of like dynamic hot loading of a function can really frustrate your static analysis, because if you want to find, for example, cross-references to that function, go through, like update the pointer, and then check your cross-references to it. FireEye actually did a nice blog post where they demonstrated how to do this using the C-tree API of IDA Pro. And so we implemented a similar sort of functionality, and so there's now like this load dynamic imports button down here. And so if I click that, it's actually going to look for all of the calls, and you'll notice up here this list has now changed. There's no ordinal numbers anymore, because now it just says DYN. These are dynamic functions. And so these are all the dynamic functions that were loaded. They would have been loaded dynamically. Again, we're not running the binary. We're just sort of analyzing it statically to figure out where are the places where are the global pointers that were updated with calls to getProcAddress, what were the string arguments to getProcAddress at that point, annotate that function pointer, and then, and this is the interesting part that actually helps make your life better, go find all the cross-references to that particular call through that function pointer. And so now we've got a list over here in our cross-references to all these dynamic functions, right? So without even doing a sort of full analysis of the binary, and it's also worth pointing out that the triage mode does a like really cursory analysis. It only does the sort of intermediate language analysis that it needs to answer particular questions. So it's much quicker than the normal full, like give me all the ILs. We've got a list of all the cross-references. So we'll do one last one. Oh, the crypto scanner I'm actually going to do on the command line, because one of the nice things here is that we can just script up and batch automate across a bunch of samples. And so this was, I forget which malware sample this one was, but it's going to load it up, analyze the IL, look for all the crypto constants, and you're going to see I've already got the output over here from before, so you can see it's going to give you the address, the name of whatever the crypto constant it found was, the actual bytes, the family of crypto, and you can throw that up and put it in some kind of batch automation to be able to extract all these constants. And again, the goal there is that you can do it regardless of architecture. All right. Here's the link to the URL for the slides. The slides have a bunch of other notes. If you have any other questions about the ILs, I'd love to talk about them afterwards. Otherwise, thank you very much for your time.